antimatter. It sounds like something straight out of science fiction, a dangerous, forbidden energy source locked away in the vaults of physics. But it isn't fiction, it's real. It's one of the strangest, most mysterious discoveries humanity has ever made. And it might just be the most explosive idea in the universe. To understand antimatter, we have to rewind to one of the most revolutionary breakthroughs in science. When physicists first realized that everything around you, everything you've ever touched, seen, or felt, is made of tiny particles. Atoms, electrons, protons, neutrons. These are the building blocks of reality. Now, imagine you had a mirror universe. Not just a reflection in glass, but an actual physical counterpart to every single particle. An electron has an opposite twin called a positron. Proton has an antiproton. Neutrons have antineutrons. Put them side by side, they look the same. Same mass, same spin, but their charges are reversed. Where the electron is negative, the positron is positive. Where the proton is positive, the antiproton is negative. And here's the kicker. If matter and antimatter ever touch, they annihilate each other. They don't bounce, they don't merge, they don't repel, they disappear. All of their mass gets instantly converted into pure energy, according to Einstein's famous equation, E mc2. Think about that for a moment. Nuclear bombs, like the ones dropped on Hiroshima and Nagasaki, release energy by splitting, atoms fission. Hydrogen bombs release energy by fusing atoms, together fusion. But both of those methods only release a tiny fraction of the mass energy locked inside, matter. Antimatter is different. It's total, absolute. When a particle meets its antiparticle, there's no leftover fuel, no nuclear waste, no fragments. 100% of the mass transforms into energy. That makes it the most efficient explosive imaginable. How much energy, you ask? Let's put it into perspective. 1 gram of antimatter colliding with 1 gram of matter releases about the same energy as the atomic bomb that destroyed Hiroshima, 15 kilotons of TNT, a kilogram of antimatter. That equals about 43 megatons of TNT, which is almost the size of the most powerful nuclear weapon ever detonated, the Tsar Bomba, built by the Soviet Union in 1961. And that was so large, they couldn't even test it at full power. And here's the terrifying part. Unlike nukes, antimatter leaves no radioactive fallout. It's clean annihilation. No lingering poison, just raw destruction. But let's not get ahead of ourselves. Before antimatter became the ultimate sci-fi doomsday device, it started as a mathematical curiosity. In 1928, British physicist Paul Dirac was trying to solve one of the great puzzles of physics: how to describe the behavior of electrons at high speeds, close to the speed of light. He wrote down an equation, a kind of fusion between quantum mechanics and Einstein's relativity. At first it looked wrong. The math suggested something strange. Electrons should have counterparts with the same mass but with opposite charge. At the time, no one had seen such a thing. Dirac hesitated. Was it just a mathematical artifact, a glitch in the equations? Or was it pointing to something real? He boldly predicted there must exist a new kind of particle, the anti-electron. And then in 1932 it was discovered. Carl Anderson, working with cosmic rays in California, found tracks in his cloud chamber that didn't match electrons or protons. They curved in the wrong direction in a magnetic field. It was the positron, the very particle Dirac's equation had predicted. Antimatter wasn't just math. It was real. This discovery shook physics to its core. It meant the universe had an opposite side, a hidden twin. For every piece of matter there could exist antimatter, a mirror universe lurking behind the veil. But here's the mystery. When we look at the cosmos, we see stars, planets, galaxies, all made of matter. Where's all the antimatter? If the Big Bang created equal amounts of matter and antimatter, then shouldn't the universe have annihilated itself instantly? Shouldn't we be living in a void of pure radiation? And yet we're here. Somehow matter won. This imbalance, why matter dominates the universe, is still one of the greatest unsolved puzzles in physics. Somewhere in the very beginning of time, nature broke the symmetry. One extra particle of matter survived for every billion particles annihilated, and that tiny imbalance became everything. Us, Earth, the stars. Without it, we wouldn't exist. So antimatter is not just explosive fuel. It's a cosmic mystery, a riddle written into the fabric of the universe. Today, we can actually make antimatter. Laboratories like CERN can produce antiprotons in high-energy collisions. Hospitals use positrons every day in PET scans, positron emission tomography, to detect cancer and study brain activity. In fact, every time a positron is released in your body during one of these scans, it annihilates with an electron, producing gamma rays that doctors can detect. But here's the problem. Antimatter is ridiculously hard to produce and store. Right now, making a single gram of antimatter would cost, wait for it, about $1 trillion. That's because you need enormous accelerators, smashing particles at nearly the speed of light. And then you have to trap the antimatter in sophisticated magnetic fields so it doesn't touch any normal matter. Even the walls of a container would destroy it. So far, the total amount of antimatter ever produced by humans is about a few nanograms. That's less than a speck of dust, enough to power a light bulb for a few minutes, if you could somehow use it efficiently. So the idea of antimatter bombs? For now, that's fantasy, but let's play a thought experiment. Imagine a future where technology advances far enough that we can mass-produce antimatter, perhaps mining it from space. Did you know? NASA once speculated about spacecraft powered by antimatter engines. In theory, it's the most efficient fuel possible. A tiny pellet of antimatter could send a probe to another star faster than anything we can dream of today. No fuel known to science can compete. That's why in Star Trek, warp drives run on antimatter. In Angels and Demons, an antimatter bomb threatens to vaporize the Vatican. In countless video games and novels, antimatter shows up as the weapon of last resort. The perfect balance of science, fact, and fiction. But let's be clear, antimatter is not some fantasy material. It's real. It's measurable. It's been created, stored, and studied. Right now, scientists at CERN can hold antihydrogen atoms for several minutes in magnetic traps. Just think about that. Humans have literally bottled pieces of the mirror universe, tiny, fragile droplets of the cosmos's shadow. So what is antimatter? It is the universe's twin. It is nature's mirror image. It is the purest fuel imaginable and the most destructive weapon conceivable. It's science fact that feels like science fiction, but in the wrong hands or even in the right hands used carelessly, it could be catastrophic. A teaspoon of antimatter could flatten a city. A kilogram could burn a nation. A ton could crack the earth apart. We are far, far away from such power, but the idea alone haunts us. Because history has shown us, whenever humanity discovers a new source of energy, we use it. Fire became weapons, gunpowder changed war, nuclear fission gave us Hiroshima. So what happens when we unlock the energy of total annihilation? This is the question that hangs over antimatter. Is it the fuel of our interstellar future, or the bomb that ends our story? Antimatter. The word itself sounds like forbidden science, an exotic force hidden in the vaults of physics. And yet antimatter isn't fiction. It's real, tangible. And it might just be the most explosive idea the universe has ever revealed. To understand antimatter, let's take a step back. Everything you see, your body, your phone, the air you breathe, the stars in the sky, is made of tiny building blocks, atoms. Inside those atoms are electrons, protons, and neutrons. This is matter, the stuff of everyday reality. Now imagine a mirror universe, not a reflection in glass, but a perfect cosmic twin. For every particle of matter, there exists an opposite. The electron's mirror is the positron. The proton's twin is the antiproton. Even the neutron has its own counterpart. And here's where it gets strange. These opposites look identical in mass and spin, but their charges are reversed. Where an electron is negative, the positron is positive. Where a proton is positive, the antiproton is negative. They are reflections, perfect inversions of the particles that make up our world. But the real shock comes when matter and antimatter meet. They don't collide like billiard balls. They don't fuse like atoms in a star. They annihilate, instantly. The entire mass of both particles vanishes, converted into pure energy. This is where Einstein's most famous equation comes alive, E, mc2. A tiny speck of mass, multiplied by the speed of light squared, becomes a fireball of unimaginable energy. To put that in perspective, 1 gram of antimatter colliding with 1 gram of matter unleashes the energy of the Hiroshima bomb, 15,000 tons of TNT. A kilogram? 43 megatons. That's bigger than the Tsar bomber. the most powerful nuclear device ever detonated on Earth. But here's the terrifying difference. A nuclear bomb leaves radioactive fallout. Antimatter leaves nothing. Just pure, clean destruction. No radiation. No poison, just light heat, shockwave, gone. Sounds like a weapon out of a nightmare, doesn't it? But before antimatter was the stuff of doomsday theories, it was just a mathematical curiosity. In 1928, a British physicist named Paul Dirac was trying to solve a problem: how to describe electrons moving close to the speed of light. His math, what we now call the Dirac equation, predicted something bizarre. It suggested that for every electron, there must exist an opposite version with the same mass, but a positive charge. At first, it seemed absurd. No one had ever seen such a particle. Was it just a glitch in the math? But in 1932, the impossible became real. Carl Anderson, studying cosmic rays, found strange tracks in his detector, particles curving in the wrong direction in a magnetic field. They weren't electrons. They weren't protons. They were positrons. The anti-electron Dirac's wild prediction had been proven. Antimatter existed, and with that the universe cracked open. If every particle had a twin, then what if? Entire stars, galaxies, even whole universes could be made of antimatter. But if that were true, where are they? Because when we look out into the cosmos, all we see is matter, stars, planets, gas, dust. Where's the antimatter? If the Big Bang made equal amounts of matter and antimatter, then the universe should have annihilated itself in a flash of pure energy. And yet, here we are, somehow matter won. This imbalance, the question of why matter dominates antimatter, is still one of the greatest mysteries in physics. Without it, we wouldn't exist. Every breath you take, every star you see in the night sky, is the result of that cosmic imbalance. Today, we can actually create antimatter in laboratories. At CERN, scientists collide particles at near light speed and outpop antiprotons. Hospitals use positrons every day in PET scans, positron emission tomography, to detect cancer. In fact, every time a positron is released inside your body during a scan, it annihilates with an electron, producing gamma rays that doctors can measure. But here's the catch: producing antimatter is insanely difficult. Right now, creating just 1 gram would cost around $1 trillion. And storing it? Even harder. Antimatter annihilates on contact with matter, so you can't keep it in a jar. You have to suspend it in vacuum chambers, held by magnetic traps. The tiniest leak, the smallest touch, and it's gone, in a flash of energy. So far, the total amount of antimatter ever produced on Earth is less than a speck of dust. Enough to power a light bulb for a few minutes. That's it. Humanity has bottled the universe's shadow, but only in droplets. And yet, the possibilities are endless. Imagine spacecraft powered by antimatter engines. A few grams could propel a ship to another star. NASA has even studied the idea. Imagine medical treatments that use antimatter to destroy tumors with pinpoint precision. And yes, imagine bombs the size of marbles that could erase entire cities. Science fiction has seized on this duality. In Star Trek, antimatter fuels warp drives. In Dan Brown's Angels and Demons, a canister of antimatter threatens to obliterate the Vatican. In countless stories, it's the weapon of last resort, the fuel of ultimate destruction, because that's what antimatter is: nature's mirror. The twin of everything that exists, the purest source of energy we can imagine, and the most dangerous. But perhaps the most haunting truth is this: history shows us that whenever humanity unlocks a new energy source, we use it: fire, gunpowder, nuclear fission. So what happens when we finally master antimatter? Will it take us to the stars or bring our story to an end? In Chapter 1, we uncovered the strange, almost mythical nature of antimatter, an invisible twin of our world, capable of releasing unimaginable power when it touches ordinary matter. But now we ask the darker question: could antimatter be weaponized? Could it become the ultimate bomb, the perfect tool of war? To understand the terror of this question, remember how the atomic bomb reshaped human history. In 1945, when the mushroom clouds rose over Hiroshima and Nagasaki, humanity entered a new age. For the first time, a single weapon could annihilate a city. That power came from splitting atoms, fission. Just a fraction of matter's mass was released as energy. But antimatter doesn't release a fraction. It releases everything. Every ounce of its mass becomes energy. No radioactive waste. No lingering fallout, just pure annihilation. So a baseball-sized lump of antimatter would carry the energy of the largest nuclear weapon ever detonated on Earth, and it would fit in the palm of your hand. In theory, an antimatter warhead would be the most compact, efficient, and terrifying weapon ever built. Unlike a nuclear device, there would be no heavy uranium or plutonium cores, no giant reactor to refine the material, just a tiny capsule of antimatter suspended in a magnetic bottle waiting to be released. Imagine a bomb dropped from orbit. On impact, the containment fails. The antimatter touches matter, and in a flash, the city below is gone. No fallout, no radioactive ash, just fire, shockwave, and silence. But here's the paradox. Despite its terrifying potential, antimatter is almost impossible to weaponize today. Producing even a nanogram costs millions of dollars. To build a single bomb, you'd need grams, billions upon billions of dollars worth of antimatter. Entire power plants dedicated to making a few particles at a time. And then comes the hardest part, storage. Antimatter can't touch anything. The moment it grazes ordinary matter, it annihilates. To keep it contained, you need elaborate magnetic traps running flawlessly for days or years. A power failure, a tiny crack in the system, and your weapon detonates on the spot. That makes antimatter less of a bomb and more of a suicide device. So if the physics are real, but the engineering impossible, why does antimatter terrify us so much? Because even if we can't build these weapons today, the potential is there. The physics says it's possible. And when physics says something is possible, history suggests humanity eventually finds a way. Science fiction has already imagined it. In Star Trek, antimatter isn't a weapon. It's fuel powering warp drives to explore the stars. But just beneath the surface, the implication is chilling. That same energy could level worlds. In Dan Brown's Angels and Demons, terrorists threatened the Vatican with a stolen canister of antimatter. Just a few drops, enough to erase half of Rome. In countless novels, antimatter becomes the weapon of last resort, a doomsday device hidden away until the final act. Why does fiction love it so much? Because antimatter is the perfect hybrid of real science and imagination. It exists, it's proven, it's been created in laboratories. And yet it feels almost mythical, like bottled lightning or a genie in a lamp. But let's push this thought experiment further. Imagine a future 50 years from now. Fusion power has been mastered. Space travel is routine. Particle accelerators the size of cities churn out antimatter by the gram. Militaries race to build the first antimatter bomb. The weapon isn't dropped from planes. It's hidden in suitcases, smuggled into cities, launched from satellites. A device the size of a coffee cup could erase a metropolis. There is no defense, no shield, no counterattack. The moment antimatter touches the world, it's already too late. This is why some scientists quietly warn, if we ever learn to mass-produce antimatter, the genie will be out of the bottle. Unlike nuclear weapons, which require enormous reactors and enrichment facilities, antimatter weapons could, at least in theory, be produced in smaller, more portable quantities. That makes them even more frightening. And here's the nightmare scenario. What if antimatter isn't just used in bombs, but in bullets? Imagine a rifle round containing micrograms of antimatter, held in a magnetic sheath. The moment it strikes a target, it annihilates, not with a bang, but with a flash brighter than the sun. Impossible today, but tomorrow, who can say? But perhaps the greater danger isn't just war. It's accidents. Right now, the antimatter created at CERN is held in magnetic traps. If containment fails, even a few nanograms would release a violent flash of gamma radiation. Nothing catastrophic, but scale that up and the risk becomes existential. What happens when a spacecraft carrying antimatter fuel malfunctions in orbit? What happens if a rogue state or group gains access to antimatter storage? What happens if the quest for energy leads us down the same path that nuclear fission did in the 20th century, toward weapons before peace? So, could antimatter be a weapon? The answer is simple and terrifying, yes. The laws of physics make it possible. The only barriers are cost, technology, and control. For now, those barriers protect us. For now, antimatter is more of a dream than a threat. But history whispers a warning. In 1939, fission was just a laboratory curiosity. By 1945, it had leveled 2 cities. In the same way, antimatter may one day leap from scientific experiment to weapon of war. And when that day comes, humanity will face a choice: use it to reach the stars, or to erase them. When we talk about the great mysteries of the universe, antimatter feels exotic but familiar. We've created it in laboratories, we understand its properties, and we know just how dangerous it could be if harnessed. But dark matter is different. Dark matter is not just strange, it is unknown. It is invisible, untouchable, and it surrounds us at every moment. We cannot see it, we cannot feel it, but without it, the universe as we know it would simply fall apart. This is the story of dark matter. The discovery began with a puzzle. Back in the 1930s, astronomers studying galaxies noticed something strange. The stars at the edges of galaxies were moving far too quickly. According to the known laws of gravity, those outer stars should have been flung into space, like droplets of water spinning off a wheel, but they weren't. Something invisible seemed to be holding them together. Decades later, in the 1970s, the astronomer Vera Rubin mapped galaxy rotations with incredible precision. Her work confirmed the mystery. Galaxies weren't behaving as expected. They were spinning as if they contained far more matter than what could be seen with telescopes. The conclusion was inescapable. Something invisible, something massive was exerting gravity. Scientists named it dark matter. Today, we believe dark matter makes up about 27% of the universe. Compare that to normal matter, the stuff that makes up stars, planets, you and me, which accounts for only about 5%. Everything we have ever studied, every atom, every molecule, all the shining stars in the sky, make up less than a 20th of the cosmos. The rest is hidden. Dark matter doesn't emit or reflect light, and it doesn't interact with electromagnetic forces, which means our telescopes, no matter how powerful, will never be able to see it directly. We can only detect it through its gravitational pull, the way it bends the motion of galaxies, the way it distorts light passing through it. And yet, despite its invisibility, dark matter may be passing through us right now. Billions of dark matter particles could be streaming through your body every second, moving through the walls, the Earth, the very core of our planet, without leaving a single trace. It is like a ghostly substance, a hidden fabric layered on top of the universe we know, shaping the cosmos without ever revealing itself. What exactly is it? Some scientists propose exotic particles, others suggest whole hidden structures, dark stars, dark planets, even entire dark galaxies orbiting alongside our own, completely invisible. Science fiction has long imagined such shadow universes, and for once fiction may be brushing against fact. If dark matter could ever be harnessed, the possibilities and the dangers are staggering. In theory, dark matter could slip through walls, armor, or shields, ignoring the barriers that protect us. In science fiction, this becomes the foundation for terrifying weapons. Warships firing invisible projectiles of dark matter that pass straight through defenses before triggering gravitational collapse, or bombs that seed dark matter into a planet's core, twisting its gravity until the world itself cracks apart. These are only speculations, but so were nuclear weapons in the early 20th century. The idea of unleashing the unseen as a weapon is both thrilling and terrifying. For now, the reality is more humbling. We still don't know what dark matter actually is. We have built massive underground detectors, some the size of swimming pools filled with liquid xenon, shielded deep beneath mountains to catch a single collision between dark matter and normal matter. So far, the detectors remain silent, and yet the evidence is everywhere. Galaxies rotate too fast. Light bends mysteriously as it crosses space. The universe whispers that dark matter is real, even if it refuses to show itself. In truth, dark matter is the skeleton of the universe, the scaffolding on which all galaxies hang. Without it, stars would scatter, galaxies would tear apart, and the cosmos would be formless. With it, there is structure, there is balance, and there is order. It is the greatest unseen force in nature, and perhaps one day the greatest tool or greatest weapon our species will ever encounter. Antimatter showed us the power of destruction. Dark matter shows us the depth of mystery. But beyond even this hidden mass lies something stranger still. A force not holding the universe together but pushing it apart. That force is dark energy. If dark matter is real, and all evidence points to the fact that it is, then it becomes impossible not to ask, could it be used? Could this hidden mass, this invisible skeleton of the universe, ever be harnessed as a tool, or even as a weapon? For scientists, the question is almost unanswerable. We don't yet know what dark matter is, let alone how to control it. But for science fiction, this ignorance is a gift. It creates a canvas where writers, filmmakers, and dreamers can imagine technologies and dangers that stretch beyond the limits of what we know. In many stories, dark matter becomes the perfect material for futuristic weapons. Because it does not interact with light or normal matter in the way atoms do, it could, in theory, pass straight through barriers that would normally block or deflect attacks. Imagine a starship armed with dark matter cannons, firing invisible projectiles that ignore shields, armor, and fortifications. The target sees nothing, feels nothing, until gravity itself begins to twist and collapse under the sudden weight of the invisible strike. The weapon would not simply damage, it would destabilize the very forces that hold matter together. Science fiction also imagines bombs built around dark matter. In this vision, dark matter is seeded into the core of a planet or star. Slowly, its hidden mass begins to warp gravity, pulling at the planet's structure. Oceans shift, tectonic plates crack, mountains rise and collapse, and finally the world gives way, torn apart by a force that cannot be seen or stopped. In such a scenario, dark matter is not just a weapon of destruction, it is a weapon of unmaking, a cosmic tool capable of rewriting the destiny of entire worlds. But the possibilities extend beyond destruction. Some imagine dark matter as a shield rather than a sword. Because it passes through normal matter, a civilization capable of manipulating dark matter might weave invisible walls of it, bending space itself around cities or starships, creating cloaks that no telescope could penetrate. Others envision transportation systems based on dark matter, engines that use its hidden mass to distort gravity wells and allow faster-than-light travel. In these stories, dark matter is not only dangerous, it is liberating, the key to unlocking new forms of exploration. There is also a more unsettling idea. What if dark matter is not something to be harnessed at all, but something already being used? If entire galaxies are wrapped in halos of dark matter, who is to say that some advanced civilization has not already learned how to manipulate it? To us, the galaxies look natural, their shapes dictated by invisible mass. But what if some of those structures are not natural at all? What if they are the fingerprints of alien engineering on a cosmic scale? Whole civilizations shaping galaxies with the mastery of dark matter. These ideas remain speculative, of course, but that is what makes them so compelling. Science fiction thrives on the unknown, and dark matter is the greatest unknown of all. It is invisible, untouchable, and yet it holds galaxies together. If humans ever learned to manipulate it, the balance of power in the universe would change forever. Wars would not be fought with metal or fire, but with gravity and shadows, with weapons that cannot be seen, only felt. And yet there is a haunting irony here. Dark matter has remained hidden for billions of years, content to shape the universe silently, never revealing itself. Perhaps it is meant to remain that way. Perhaps it is a reminder that not everything in the cosmos was meant to be controlled, and that some mysteries are safer left unsolved. But if history has taught us anything, it is that humanity will always reach for the forbidden, and if dark matter can be turned into a weapon, one day someone will try. If dark matter is the invisible glue that holds the universe together, then dark energy is its opposite, the force that tears it apart. Unlike antimatter, which we can create in laboratories, or dark matter, whose existence we infer through gravity, dark energy is even more elusive. It was not discovered through direct experiments, but through something far more unsettling, the realization that the universe itself was behaving in a way no one expected. For decades, scientists assumed the universe's expansion, set into motion by the Big Bang, must be slowing down. Gravity, after all, pulls matter together. And with all the galaxies, stars, and hidden dark matter scattered across the cosmos, the assumption was that this collective mass would gradually slow the outward rush of the universe. Perhaps given enough time, it might even reverse, collapsing everything back into a fiery Big Crunch. But in the late 1990s, two independent teams of astronomers studying distant supernovae made a shocking discovery. The light from those exploding stars revealed that the universe wasn't slowing down at all. It was speeding up. Something was pushing galaxies apart with more and more force over time. This wasn't just unexpected, it was revolutionary. To explain it, scientists proposed a mysterious, repulsive energy filling all of space, an energy that counteracts gravity and accelerates the expansion of the cosmos. They called it dark energy. Today, dark energy is believed to make up nearly 70% of the universe. Think about that for a moment. The overwhelming majority of everything in existence isn't matter. Isn't light, isn't even dark matter. It's something even more mysterious. An invisible pressure woven into the very fabric of space itself. It does not shine, it does not pull, and it cannot be bottled or touched. Instead, it pushes, quietly, relentlessly. It stretches the universe wider and wider, and the further galaxies are, the faster they recede from us. The implications are staggering. If dark energy continues its work unchecked, the universe will not slow down or collapse. It will expand forever. Over billions of years, galaxies will drift farther apart until they vanish from view. Stars will burn out, worlds will freeze, and eventually the universe could become a cold, dark, empty void. A lonely wasteland where every light has been pulled away into unreachable distance. Scientists call this fate the heat death or the big freeze, and at its heart lies dark energy. But the mystery runs deeper. What is dark energy? No one knows. Some suggest it is a property of empty space itself, a cosmological constant that Einstein once proposed, then rejected, only for it to return decades later as the leading explanation. Others think it may not be constant at all, but a dynamic evolving field that changes over time, reshaping the universe in ways we cannot yet predict. A few even wonder whether dark energy hints at flaws in our understanding of gravity itself, suggesting that Einstein's theory of relativity, so successful in describing the cosmos, might not be the full story after all. And in the realm of science fiction, dark energy becomes a playground for the imagination. If it truly exists everywhere in all space, then perhaps it could be tapped like an endless well of power. Futuristic civilizations might build engines that harness dark energy to warp space, bending the expansion of the cosmos to their will. Others might weaponize it, creating fields of accelerated expansion that rip enemies apart at the atomic level, or bombs that unleash miniature big bangs within the confines of a star system. In such visions, dark energy is no longer the silent driver of cosmic fate. It is the ultimate tool of creation and destruction. Yet, even as we speculate, the truth is sobering. Dark energy is not just a theoretical curiosity. It is real. It is here right now, stretching the space between every atom, every star, every galaxy. It is the invisible hand guiding the ultimate destiny of the universe. And for all our scientific brilliance, we are powerless before it. We can measure its effects. We can calculate its role in cosmic expansion. But we cannot stop it, cannot touch it, and cannot hope to contain it. Dark energy is the most dominant force in existence. It defines the fate of the cosmos itself. And for now, it remains a mystery, perhaps the greatest mystery of all. If dark matter is the ghostly scaffolding of the universe, then dark energy is its restless heartbeat, the force that drives expansion and reshapes the destiny of everything. Scientists see it as an enigma, something beyond our reach. But in the realm of science fiction, dark energy becomes the ultimate frontier, a limitless reservoir of power and a terrifying weapon unlike anything else in the cosmos. Imagine, for a moment, a civilization advanced enough to understand and control dark energy. They would not just harness electricity or nuclear fusion, they would command the very fabric of space itself. Dark energy is everywhere, in every corner of the universe, seeping through every atom and galaxy. If it could be tapped, it would provide an infinite power source, a cosmic fuel that never runs out. Starships powered by dark energy engines might bend space at will, riding the accelerating expansion of the universe to leap across unimaginable distances. Travel between galaxies, normally impossible, could become routine. What we see as an unstoppable expansion could instead be transformed into a highway for exploration. But with great power comes the inevitable shadow of war. Dark energy, turned into a weapon, would make nuclear bombs look like firecrackers. In one vision, dark energy warheads create localized zones of accelerated expansion, tiny regions where space itself stretches uncontrollably. Anything caught inside would be ripped apart at the atomic level, unraveling into scattered particles before vanishing entirely. In another, military scientists might design vacuum destabilizers, devices that trigger violent fluctuations in the very energy of empty space, unleashing chain reactions that consume entire planets, systems, or even stars. Science fiction also imagines more subtle, almost godlike uses of dark energy. A weaponized dark energy field might not destroy a planet directly, but instead manipulate the rate of time within it. Imagine an enemy world trapped in a bubble, where time races forward 1,000,000 times faster than the outside universe. Within moments, its people would wither into dust, its cities would crumble, its oceans would dry, centuries of destruction unfolding in the blink of an eye. Or perhaps the opposite. Time slowed to near stillness, freezing entire armies in place, their weapons useless against the invisible hand of cosmic acceleration. On the grandest scales, dark energy could be the ultimate tool of cosmic engineering. An advanced civilization might use it not only to conquer enemies, but to shape entire galaxies. They could herd stars, stabilize black holes, or collapse rival civilizations into unreachable pockets of space. For them, wielding dark energy would be like sculpting clay, with reality itself as their canvas. And for anyone standing against them, resistance would be futile. They would be fighting the universe itself. And yet, even in these fantastical scenarios, dark energy carries a haunting danger: unpredictability. Unlike antimatter, which can be understood in terms of mass and energy, or dark matter, which is bound by gravity, dark energy is poorly understood even in theory. To tamper with it might mean unleashing forces far beyond control. A single miscalculation could destabilize not just a battlefield, but an entire galaxy. The weapon would not only destroy enemies, it could unravel the universe itself. This is why in many stories, dark energy weapons are portrayed as forbidden, outlawed, or locked away in ancient vaults. They represent the temptation of limitless power paired with the certainty of ultimate risk. For us today, these ideas remain fiction. We have no means of touching dark energy, no tools to manipulate it, and no theories solid enough to suggest how it might be controlled. But the very fact that 70% of the universe is made of it means the potential is staggering. Science fiction takes this fact and pushes it to its extreme. What if we could use it? What if we could fight wars with it? What if our fate, or the fate of the universe itself, rested on who could control the acceleration of space? It is a terrifying question, but it is also a captivating one. And it reminds us of something deeper, that our greatest stories often spring not from what we already know, but from the mysteries we can barely begin to understand. Throughout history, science fiction has thrived on mysteries. The unknown becomes a playground, a blank canvas upon which writers, filmmakers, and dreamers sketch stories of wonder and terror. Antimatter, dark matter, and dark energy are no exceptions. Each has already made its way into some of the most iconic works of science fiction, shaping battles among the stars, futuristic technologies, and visions of humanity's future. Antimatter, perhaps the most accessible of the three, has been a staple in science fiction for decades. Star Trek famously used it as the fuel for warp drives, stored in magnetic containment fields, and released in controlled annihilations to generate near-infinite energy. In other stories, antimatter becomes a terrifying weapon. Dan Brown's novel Angels and Demons imagines a hidden vial of antimatter, threatening to obliterate Vatican City. In video games, antimatter bombs serve as the ultimate superweapon, feared for their unstoppable power. Audiences instinctively understand the danger. Matter itself, the fabric of reality, becomes volatile in the wrong hands. Dark matter, on the other hand, represents something more mysterious, and so its role in fiction often leans towards shadow and intrigue. In many novels and films, dark matter is imagined as a hidden substance, an invisible veil masking entire worlds or fleets. Some depictions treat it as exotic fuel for starships, allowing journeys across impossible distances. Others envision it as a weapon, shells of invisible mass that strike with crushing gravity. Because dark matter cannot be seen, its very invisibility makes it the perfect metaphor for unseen threats, secret powers, and the lurking dangers of the cosmos. Dark energy is perhaps the most speculative, but it has also found its place in storytelling. Writers often portray it as the ultimate power source, something vast and inexhaustible, capable of bending the laws of space and time. In certain stories, it becomes the basis for engines that distort the expansion of the universe, enabling faster-than-light travel. In darker tales, it is weaponized. Bombs that tear holes in space, fields that accelerate destruction, or tools of godlike civilizations who sculpt galaxies with ease. Dark energy is harder to grasp than antimatter or dark matter, but its very strangeness makes it compelling. It embodies mystery, destiny, and the inescapable pull of forces beyond human control. Taken together, these three concepts form a kind of trilogy in science fiction. Antimatter represents energy, the fire we can harness, the spark that can destroy. Dark matter represents mystery, the unseen foundation that both supports and threatens us. Dark energy represents fate, the unstoppable expansion, the force that defines the endgame of the cosmos. Each of them resonates with audiences because they speak to something deeper than science. They remind us that the universe is vast, full of forces we barely comprehend, and that human ambition will always push us to try and control them. What is perhaps most fascinating is how these ideas move between science and story. Real discoveries inspire fiction. Vera Rubin's work on galaxy rotations fuels tales of invisible matter. The discovery of cosmic acceleration gives birth to visions of universal expansion weapons. In turn, fiction sparks curiosity in the next generation of scientists who look at these mysteries and ask, what if? It is a feedback loop between imagination and reality, one that has carried us from the dream of rockets to actual space travel, from fantasies of splitting the atom to the terrifying reality of nuclear weapons. And so, in books, films, television, and games, antimatter, dark matter, and dark energy live not just as scientific puzzles, but as symbols of our curiosity and our fear. They are the shadows at the edge of our understanding, the sparks of power we dream to control, and the whispers of futures both bright and catastrophic. They remind us that science fiction is not just about what we know, it is about what we don't know, and how we imagine filling the gaps. For all the speculation, for all the breathtaking imagination of science fiction, the truth remains: antimatter, dark matter, and dark energy are not just story devices. They are real. They exist in the equations, in the evidence, in the data we measure from stars and galaxies. And right now, across the world, scientists are working tirelessly to uncover their secrets. Antimatter is the one we understand best, though it remains as dangerous as it is fascinating. In laboratories such as CERN, particles of antimatter are created in high-energy collisions inside particle accelerators. Researchers trap tiny amounts of antihydrogen in magnetic cages, studying how it behaves compared to normal matter. The amounts produced are minuscule, nanograms at most, but even those are enough to revolutionize our understanding of physics. Antimatter research may one day lead to technologies in medical imaging, propulsion, or energy generation. But the same research also reminds us of its danger. Release too much at once and the result is devastating annihilation. The search for dark matter, however, is far more elusive. Because dark matter does not interact with light, scientists cannot see it directly. Instead, they build massive detectors hidden deep underground, far from cosmic radiation, to watch for the faintest hint of a collision between dark matter and ordinary atoms. These detectors, filled with ultra-pure liquids like xenon, wait in silence for a single event that would prove dark matter's existence in the lab. So far, the silence has stretched on. The universe whispers of dark matter in its cosmic behavior. But down here on Earth, it slips past our instruments like a ghost. Still, the hunt continues, because if we could find dark matter, it would open a new chapter in physics, a doorway into the hidden structure of the cosmos. Dark energy is perhaps the greatest mystery of all, and the most difficult to probe. Unlike antimatter or even dark matter, it cannot be captured or contained. Instead, astronomers study its effects on the scale of the entire universe. By measuring how galaxies move, how light from distant supernovae travels through space, and how the cosmic microwave background ripples with ancient echoes, scientists can trace the fingerprints of dark energy. Powerful telescopes like the Vera C. Rubin Observatory and space missions like the Euclid Telescope are being designed to map billions of galaxies, hoping to reveal how dark energy has shaped cosmic expansion over billions of years. Each observation adds a piece to the puzzle, but the full picture remains out of reach. What unites all these efforts is the sense of humility. Our species has walked on the moon, sent probes to the edge of the solar system, and split the atom, but when it comes to the vast majority of the universe, we are still in the dark. Antimatter, dark matter, and dark energy are reminders that most of reality is hidden from us. Scientists are not only chasing answers to questions, they are redefining what the questions even are. Are these forces separate or are they connected? Is dark energy a property of space itself, or is it something deeper? a sign that our entire theory of gravity is incomplete. Could antimatter and dark matter hold clues to why the universe exists at all instead of nothing? Each experiment, each observation, is a step into the unknown. And just like the science fiction stories we tell, the real journey is as much about the search as it is about the answers. The universe is keeping secrets, but with each generation we come closer to pulling back the veil. Science is not just about discovery, it is about responsibility. And when it comes to forces as vast and mysterious as antimatter, dark matter and dark energy, the ethical questions loom as large as the science itself. If humanity were ever to control these forces, what would that say about us? What kind of civilization would we need to become to wield them wisely? Take antimatter, for instance. On one hand, it could be a dream, an energy source with nearly limitless potential, capable of fueling interstellar journeys, eliminating pollution, and ending our dependence on fossil fuels forever. But on the other hand, it could become the ultimate weapon of mass destruction, far beyond nuclear fire. The same particle that heals in a PET scanner could in sufficient quantities obliterate entire cities. The philosophical question here is not whether we can harness antimatter, but whether we should. Does humanity, with its long history of conflict and greed, deserve such power? Dark matter raises different concerns. Its very invisibility, its hidden nature makes it a perfect metaphor for secrecy and control. Imagine a future where governments or corporations monopolize dark matter technology, weaponizing its gravitational pull or using it to hide fleets, bases, or entire worlds. Ethically, we would be forced to confront questions of transparency, fairness, and survival. Who gets to decide how invisible matter is used? Would it empower all of humanity, or only a select few? Dark energy poses perhaps the most profound ethical dilemma of all. If this mysterious force truly governs the expansion of the universe, then to control it would be to play with the fate of creation itself. A civilization that could weaponize dark energy would hold the power not just to conquer planets, but to tear space and time itself apart. Would any society have the wisdom to use such power without arrogance, without corruption? Or would it inevitably lead to catastrophe, as one group or nation sought to bend the cosmos to its will? Underlying all these questions is a deeper theme, the relationship between knowledge and responsibility. History has shown us that every great discovery comes with both promise and peril. Fire brought warmth and survival, but also destruction. Nuclear power brought both energy and annihilation. Artificial intelligence even now balances between progress and existential risk. Antimatter, dark matter, and dark energy would take this balance to an entirely new level. They are not just tools. They are forces that could alter the destiny of life itself. Philosophically, they also challenge us to rethink our place in the universe. If we could wield the power of annihilation, invisibility, or cosmic expansion, what would separate us from the gods of mythology? Would we become creators, shaping galaxies with intention, or destroyers leaving only silence in our wake? The ethical question then becomes not just one of technology, but of identity. What does it mean to be human? If humanity holds the keys to forces once thought untouchable by mortal hands, in the end, these questions may be as important as the science itself. Because science gives us the how, but philosophy and ethics force us to confront the why. And in the search for answers, we might discover not just the nature of antimatter, dark matter, and dark energy, but the nature of ourselves. As we stand at the edge of knowledge, staring into the abyss of antimatter, dark matter, and dark energy, one question rises above all others. What future will we choose? Will these cosmic forces become the foundation of a brighter tomorrow, or the tools of our own undoing? The future of antimatter, for instance, could be nothing short of revolutionary. Imagine spacecraft propelled across the solar system at near light speeds, fueled not by chemical rockets but by controlled bursts of matter-antimatter annihilation. Journeys that now take decades could be reduced to years or even months. Energy crises on Earth could be solved with a single new kind of reactor, producing power without pollution. Hospitals could harness antimatter not only for advanced imaging, but for cures once thought impossible. Yet alongside this dazzling vision is the darker one. Antimatter bombs, devastating beyond imagination, wielded in wars that could erase entire civilizations in seconds. The same spark that lights the stars could extinguish us forever. Dark matter's future is even more uncertain. If scientists discover its true nature, The applications could rewrite physics itself. Invisible armor, impenetrable shields, weapons that crush enemies with unseen gravitational tides, all are within the scope of imagination. But the greater promise lies in what we cannot yet picture. Dark matter might unlock hidden dimensions of the universe, revealing new laws of nature. It could offer propulsion methods beyond even antimatter, or technologies that make invisibility itself possible. Its dangers, though, are equally profound. Imagine a military or a corporation monopolizing a resource that cannot be seen, felt, or detected, except by those who control it. The ethical nightmare would be immense. And then there is dark energy, the wildest card of them all. If humanity ever found a way to manipulate it, the possibilities would verge on godlike. Civilizations might halt or reverse the expansion of the universe, preserving galaxies from drifting apart for eternity. Others might use it to tear holes in space, creating shortcuts across the cosmos, wormholes engineered on demand. But in darker futures, dark energy becomes the weapon to end all weapons. The power to unweave space-time itself, destroying not just planets or stars, but entire swaths of reality. It is a power that would demand wisdom on a scale humanity has never demonstrated. And so, the story of these cosmic forces becomes the story of us. Will we rise to meet the responsibility of discovery, using them to expand life and knowledge across the stars? Or will we repeat the oldest patterns of history, turning wonder into weapons and brilliance into ruin? The answer lies not in the universe, but in ourselves. Yet there is hope. History also shows that humanity is capable of greatness. We dreamed of flying and built airplanes. We dreamed of reaching the moon and left footprints in lunar dust. We dreamed of harnessing the atom. And while we built weapons, we also lit entire cities with the same power. Our story has never been just about destruction. It has been about survival, about imagination, about pushing forward into the unknown. Antimatter, dark matter and dark energy are not just scientific puzzles. They are invitations. Invitations to grow, to evolve, to see the universe not as something alien and terrifying, but as a vast frontier waiting to be understood. They are the next chapter in the human story. A story still unwritten, and so we are left with a choice between hope and destruction, between wisdom and folly, between becoming wanderers among the stars or ghosts of a failed species. The universe has given us mysteries. What we do with them will define not just our future, but perhaps the destiny of all life. The question remains, when humanity finally grasps the fire of the cosmos, will we cradle it with care, or burn ourselves to ash?